As we begin talking about compounds, we're going to start off by talking about the types of bonds we might find in a compound. A couple of definitions. When we talk about a chemical bond, it's simply a force that holds atoms together or ions together in a compound. We have two kinds that we primarily talk about, although acids are sort of a third in between kind. So ionic compounds, closely packed ions of opposite charge that are stuck, the force that's holding them together is that opposites attract, or covalent compounds, which are a definite collection, also called a molecule, of atoms held together by a sharing of electrons. So sharing versus ions. Again, we could also refer to them, don't forget that the last couple chapters ago we talked about compounds being atoms of two or more different elements bonded together. So I have to have at least two elements and with a bond, but they also have to be atoms of different elements. And there's two types based off of those two bonds that we just talked about. We have molecular bonds, a group of atoms held together by a covalent bond. And remember, part of that covalent bond was talking about these definite collection. And ionic compounds, which is a set of ions of opposite charges that are held together by attraction, electrostatic attraction. And those are, ionic bonds holding the ionic compounds together. So when we really think about what is a bond, both types of bonds and all bonds are really focusing on electrostatic attraction, a fancy name for plus charges like minus charges. In our case, the plus charges are formed from protons. We're talking about protons are the source of the plus charges, and electrons are the source of the negative charges. So atoms in A, the protons in A are all clustered together and have a large positive charge that pulls on atom B's electrons in addition to atom A's own electrons. So they're not only attracted to their own electrons, but also to the electrons of nearby atoms. As long as B comes close, it can start to attract those. But that's not the only thing going on. B, similarly, has protons that are attracted to its own electrons, but also A's electrons when it gets close enough to A. So as two atoms approach, the protons in each are trying to attract the electrons in the other atom. And that's where the source of this bonding comes from. A couple of things can happen. Well, of course, you also have repulsions going on, because as they get closer, the electrons in both are repelling each other, and the protons in both are also repelling each other. So it's kind of all of these forces together, there's a happy medium in which the attractiveness is overweighing the repulsions, and we have a favorable situation in a bond. A couple things can happen. If A's protons pull on B's electrons really strongly, and B's electrons pull on A's electrons to a much weaker extent, then A can essentially rip the electrons away from B and form an ion. A would be the one that would form a negative ion because it grabs the electrons, and B would be a positive cation. Or maybe they both pull on each other's with a fairly similar pull, and they're both pulling tightly, and the electrons from the other atom are kind of brought in between them, and we call that sharing of electrons. So we can see this if we take all the possible forces, the attractive forces, but also the negative repulsions from electron, and proton, and we add all of them up together and kind of say, overall, what is the energy? So here's my energy. We talk about potential energy because we refer to that being the energy of attraction. And I see that at very short distances, when the atoms are super, super close, like on top of each other, we start to see, at the beginning, we see that big, high potential energy. It's too much energy. It's not favorable. Remember, everything likes a low energy state. But then there's a happy medium place where at just the right distance, they're close enough that that attraction is a favorable thing. If I start taking them farther away, now the proton pulls on each other, they're not as attractive, and so now it goes back up, but it's not nearly as high. So if I put them really close together, the repulsions are winning out. At a certain magic distance, they're happy. If I keep separating them, they kind of they're not really responding to each other. They're too far away. So we refer to that magic distance of the two atoms where they're favorably held together by a bond as being the bond length. So this is representing, in particular, covalent bond because I don't see any ions being formed. Nothing's happening there. So this is the hydrogen covalent compound. So again, things that we might see in chemical bonding, we talk about bond length. Again, this magical distance where they're at the right, they're close enough that the attractions are being felt, but not so close that the repulsions are becoming too much. And we talk about all of these forces of what's going on. So we have, these net potential energy is 0 point energy, which is the, when they're completely far away, we talk about that as the 0 point energy. And then there's a favorable energy at a favorable radius called R. So we have this is why atoms bond, is because it's more favorable to be together than it is to be far apart or on top of each other. So when we want to represent them, we have a couple of methods. Of course, we have chemical formulas. We've already been seeing them. We just show the symbols and we use subscripts to indicate how many. They don't tell us more than what atoms are in that molecule or what ions are in that compound. And then we start having these structural formulas. So now we're moving into more detail. We're now showing exactly where the atoms are in relationship to each other and what is bonded to what and maybe how many bonds they have. So when we draw lines in these structures, that line is representing a covalent bond. So anytime you see lines, you're thinking, okay, this is a covalently bonded structure. And we will talk about Lewis structures where they get very detailed with these covalent bonds. We also have ionic structural formulas. No lines. The bonds are simply implied by I put positive charges right next to something with negative charges. And when I see those charges of opposite charge, I know positive and negative are attracted and they're going to be stuck together. So these structural formulas tell us more information, like the arrangement of the atoms with respect to one another. And as we continue on into these Lewis structures, we can get quite a bit of information about the bonding patterns in addition and the shape and things like that. So over here we kind of see a covalently bonded structure. I see lines all over it. Here I have a little bit of a covalently, partly covalently, but then I see ions, negative ions right next to positive ions. It's implied, even though there's no lines, that the Fe2+ is ionically bonded to that structure with the oxygens with the negative charges. And then if I just put them kind of near each other, but not that close, and I have a plus sign in between, that's not indicating a structural formula. That's really just listing out components like in a chemical reaction.